Lesson 6 is all about transformations, and 6.1 starts off with rigid transformations, and we're just going to start off with definitions right away. So, a transformation means a change in position, shape, or size of a figure in a plane. So, that could be us moving it around, it could be making it bigger, making it smaller, changing its direction. Those would all be considered a transformation. And then the second line, in a transformation, the original figure is called the pre-image and the new figure is called the image. So if you were, say, given a problem, given a shape, and asked to apply transformations to it, the original problem would be the pre-image, and then the new one that you draw would be called the image. And then the third line, a rigid transformation, is when the side lengths and angle measures of a figure do not change. So basically the shape and size is staying exactly the same. Some examples of rigid transformations are translations, reflections, and rotations, and we're going to cover all of those within this 6.1 section. So the first one is translations. So the definition right here, the image has the same shape, size, and orientation. It just has a new location. So basically with translations, we're moving the pre-image up, down, left, or right. And we're just basically taking each individual point and moving it based upon those transformations. So if you look at the graphic example, it shows us taking point D and moving it 4 units to the right and then 2 units down to get, this is called D prime right here, the little like apostrophe we read as D prime, and that just represents the new point, the point of the image. And then if you look at the rest of the points, they're all just moving 4 to the right and then 2 down. They're all moving that same exact distance to get their new points, the ones that correspond with the like same point in the pre-image. So biggest thing with translations is just recognizing that we're just moving to a new location. We're not changing the shape or the size, so just moving up, down, left, or right. And then for reflection, so starting right here, the image has the same size and shape, but the location and orientation change. And then all reflections have what's called a line of reflection, which a line of reflection is equidistant from each point in the image and the corresponding point in the pre-image. I think I said pre-image and pre-image backwards, but it means the same thing. So I'm going to go ahead and just define equidistant really quick in case you haven't seen that word. So equa, like equal or equal sign, just means the same. So it's the same distance. Okay, so we have our pre-image, that's the one in blue over here. And then we have the image, which is the reflection over that line of reflection K up here. So each of the points in the image are equidistant or the same distance from the line of reflection as the point, the corresponding point in the pre-image. So like G is right here, G prime is the same distance over there. F is the distance between F and the line of reflection is right here. It's the same distance over here. So they're all the same exact distance, it's just flipped over. So I mean, you guys know like reflection or symmetry, you can kind of think of it like butterfly wings where they're symmetric on each side. But just the big thing is knowing that the points stay the same distance from the line of reflection, they just flip over it. So if they started on the left side, they would flip to the right side. And the line of reflection, it doesn't have to be like diagonal, it can be vertical, horizontal, anything. So down here is just kind of like some general reflections. So on the far left side, you can see we have K and then K prime. So it flipped down, and the line of reflection for this one was actually it flipped over the x-axis. So we read that or describe that as reflected in the x-axis, and it wouldn't be wrong to say it was reflected over the x-axis, but you will see this like reflected in specifically as like a math phrase moving forward through the rest of your math career. And then one thing to notice is that when you have a reflection over the x-axis, so if I have, say, the point xy, The only thing that changes about the points is that the y value would become negative. So they would be the same two values. Like for, it looks like if I just like kind of use this graph to get my points, this is the 0.33 because we go right 3 up 3. And then this would be the 0.3, negative 3. So the values stay the same. Your y value is just changing from positive to negative, or it would be changed from negative to positive if it flipped the other way, but keeping that same value. And then for the next one, so we have k over here, and then k prime over here. This one got reflected over the y-axis, so we read that as reflected in the y-axis. So notice here the points stay the same as well. If this is the point x, y, the only thing that would change is my x value would be negative, right? Because it's flipping over to the negative side for x. But same thing, the numbers would stay the same. My x value would just become negative. And then for the last one on the far right, so we have the point xy here, and then it reflects over this line. So it's not an axis, but it's reflecting over the line y equals x. And something kind of funny happens when we reflect over the line yx. So if you look at k to k prime over here, this was the point xy, and this is the point yx. So when we reflect over that line y equals x, the x and y coordinate just switch. So this was the point 2, 4, and then it flips over to the point 4, 2. So the x and y coordinate just switch, and then to still notice like the points are equidistant from the axis of symmetry. They're just like one, I guess, diagonal unit away. Okay, moving down to rotations. So definition down here, the measure of each angle is formed by, the measure of each angle formed by segments that connect the center of rotation to a point in the pre-image and the post-image are the same. So they have one kind of pair of segments here, but the blue one is our pre-image, the red one is our image, and I'm just going to draw like each corresponding segment or each kind of like connecting segment so we can see how the angle stays the same all the way through. So with, let's see, from the center of rotation O to B is this, and then to B prime is over here. So our center of rotation, they show between like A and A prime, and it's 130 degrees. This angle is the same size angle, it's 130. You could see it's just like a little bit like shifted counterclockwise maybe. And then same thing over here, like if I draw segments to C and C prime, it's the same size angle. This one's definitely shifted, but it's still 130 degrees. So it's just everything is getting shifted 130 degrees, kind of like it could be clockwise or counterclockwise, but it's all moving on a like similar axis basically. So they're all rotating around the same degree measurement. That one I think is a bit harder to draw unless you have one that's just like 90 degrees, 180 degrees, 270. All the ones that are just rotations of 90 degrees, those ones aren't too bad, and we'll talk about those later on in this lesson 6. Okay, moving down to 6.2, which is transformations as functions. So you can see with transformations, like there's all the wording, like rotations, translations, all that. So obviously you can write out the transformations like worded as long sentences, but there's also ways that we can shorten it. So we usually shorten the way we write transformations with something called a mapping statement. So a mapping statement can be used to describe transformations instead of writing them out as sentences. So if we look at this visual down below, we can see that we start with this point M, and we're transforming it into the point M prime. So we don't know exactly how far we're moving. It's just like in terms of variables, we don't have the actual units, but we're moving A unit to the right and then B units up. So since we're just moving to the right and to up, that would be a translation. So if we wanted to write that transformation, we would say in this graph, point M is being translated A units to the right and B units up. So if we had a bunch of problems, that would take a lot of time to write that all out. So that's why we would come in and use a mapping statement instead to write it a little bit quicker. So the mapping statement for this would be the point X, Y, and then this little symbol with like the line and the arrow is read as maps to. So maps to X plus A and Y plus B. And so since we're moving A units to the right, that's in the positive direction for X, so that's why we're adding. And then we're we're moving B units up. That's for the positive direction for Y, so that's why we're adding here. If we were moving left, you would see like X minus a number, and if we were moving down, you would see Y minus a number. And then kind of another notation that you'll see is written here down below. So it has this F colon in front of it. It's like the function F, but you'll notice everything else is the same. They have the same exact meaning. I just want you to recognize that it means the same thing regardless of if you see the F colon there in front or not. The next part, so the following graph shows the translation. Analyze the graph and the mapping statements for each point to write a general mapping statement for the transformation. So we can look at the graph and see how it's moving. We can also look at the points and see how it's moving. I'm going to show you both. You can decide which one works best for you. But we just need to grab 2 points that are corresponding. So I'm going to do F from the pre-image, F prime from the image, and see what direction and how far it's moving. So to get from F to F prime, I'm moving 4 units to the right, and then I'm moving 2 units down. So I'm going to say I'm moving 4 to the right and then 2 units down. And then we can write that with a mapping statement, instead of writing out the full sentence of translated 4 to the right and 2 down, we'll just use shorthand to write it. Before I do that, I just want to kind of show how if you were just given a set of points, you could also find how the translations worked, as long as you knew it was a translation. So for my points, if I just look at like say the first line, A and A prime, so I'm going from -2 to +2. So if I go from -2 to +2, that's going up 4, and not like up as an up or down, but just like increasing by 4. And then for my y's, I'm going from 4 down to 2, so I'd be going like down 2 or -2. And we know that our x's are controlling like left and right, so that +4 would be us going to the right 4. And then our y's are controlling up or down for our points, so that -2 is us going down 2. So it's handy to know how to do it on the graph and with points, depending on like what you're actually given in the problem. So for our mapping statement, we'll say the points x, y, those are just like the general points we're starting with. And then we'll use the maps to symbol. So this means maps to. And then we just need to describe what the like new points are. So we'll use our parentheses, and then since we write like our new points as x plus or minus a number, we need to put in another set of parentheses. So for our x values, we're going 4 to the right, or we're increasing our x values from 4. That's how we got it from the points. So we would write it as x plus 4 for 4 to the right, or you could see from the points themselves, they're going up by 4. And then our comma and another set of parentheses for the y. And then for our y values, we're going down 2, or you could see like from the set of points that everything is decreasing by 2. So since we're going down 2, we'd have to do y minus 2, close parentheses, and then don't forget to close that first set of parentheses also. So this is read as xy maps to x plus 4 and y minus 2, so that means that we're going right 4 and then down 2. So the next line, write the mapping statement for the three reflections described in 6.1. So we've already looked at this. We already know like the first one is a reflection in the x-axis, the second one reflection in the y, the third one is a reflection over the line y equals x. But we're just going to write the actual mapping statements for them now. And these are actually something that's kind of going to come in handy if you can like get a little note card or set these aside to reflect back on. That along with a few other things on this page. So for the first one, the mapping statement is we start with xy and then maps to, and then we want to describe what's happening to the points. So if you look at between k and k prime, x is staying the same. So no change is happening to x. So we don't have to describe a change there. So it would just be x, because x is staying the same. And then for y, we're going from y to negative y. So we would just have to change that y to a negative y. And you'll notice if you compare like this mapping statement to the last one that we did, we don't have to add or subtract any numbers. It's because the like value or the numbers for our points aren't really changing here because they're just reflecting. Only the signs are changing. So if only the signs are changing, or if we're only dealing with a reflection, you're not gonna like add any numbers here because you want them to keep that same number. It's just at most the sign, like the symbol in front of it, would change. So xy maps to x negative y. And then this would be a good time to kind of like maybe pause the video and like practice the next one on your own, see if you can get them, and then resume once you're ready. But for the second one, we're reflecting in the y-axis, so we're starting with xy, and then maps to, and then you'll notice on this one, like, so on our pre-image, it's x, and our image is negative x. So it's going to map to negative x. And then in our image, it's y. It stays y over here, so y stays the same. And then on our last one, so we're starting with xy. It always starts with xy, and then maps to, and we just want to look at how the points are changing. So over on our pre-image, which was k, over here, my x coordinate was x, but then on my image, my x coordinate became y. So that means that y is my new x coordinate here. And then my y coordinate is y. On the other side, on k prime, my y coordinate, like the second one, becomes x. So this would map to yx. So it just switches like the x and y coordinate, and that's what this mapping statement is telling you. So xy maps to yx. Okay, so for the next line, describe the transformation, then write the mapping statement. So there's a couple different things. If we look at the, we can't ignore the table for now. Just looking at the graph itself, you can see that the image, from the image, or sorry, from the pre-image to the image, it's rotating, like the figure is rotating. So the blue one is our image, and then it's almost like it turns down here. Like each of these points rotates around a center of rotation, which I'm going to say the center of rotation is the origin. And then remember, with rotations, we can kind of talk about like a segment that connects the points from the pre-image to the image. So like if I have a segment from the center of rotation to O, and then that segment over here to O prime, that looks like a right angle. And I'm going to test that theory with N and N prime. That's another right angle. With M and M prime, another right angle. And then with P and P prime, another right angle. So all these segments that are connecting like the point from the pre-image to the image, they're forming a 90-degree angle. So this must be a 90-degree rotation. So it's rotating 90 degrees about the origin. So if we can describe that in words, and then we'll write the mapping statement. So it's rotating 90 degrees. And when something is rotating, we want to describe the direction that it's rotating. So it's rotating this way, which is counterclockwise. So it's rotating 90 degrees counterclockwise around the origin. And then I'm going to add a couple notes to that before we move on to the mapping statement. So off to the side, just in case you ever forget like which way is clockwise and which way is counterclockwise, that's a good thing to make a note of. So for if I'm going, just draw a circle and use it that way. So if I go this way, that's kind of hard to tell. Okay, so if I go that way, that is clockwise. And then if I do the reverse, sorry, I'm really bad at drawing these. That is counterclockwise. And if those pictures don't make sense because they're not very good pictures, and if you ever forget, remember that's something that you could like really quickly just kind of Google. And I'm sure there's a lot of really pretty images comparing like clockwise and counterclockwise that look better than mine. Okay, and then the second thing I want to add is you can technically write any rotation in two different ways, or really infinite ways, but specifically in two different ways. So if I said that I rotated 90 degrees counterclockwise, I could also describe that as 270 degrees clockwise. So I basically made like one rotation 90 degrees clockwise, or I could do like 90 degrees right here, another 90 degrees right here, another 90 degrees to get that image over here, and then 90, 90, 90 would be 270 degrees clockwise. I don't really recommend writing them that way, but I just kind of want you to know that you could, and more so that you can always write rotations in different ways and still have a correct answer. Okay, so the table is here to help us see what changes are being made to our points, specifically to help us write our mapping statement. So take a second, look at the table, see if you notice a pattern. And then the things that I notice are, it looks like the X and Y's are getting switched. So we're going from, I'm gonna ignore the negatives for right now, but we're going from 4, 3 to 3, 4, 1, 3 to 3, 1, 1, 1. Well, that one's kind of hard to tell that we switched, but 2, 1 to 1, 2. So the numbers are changing. And then now I'm going to pay a little bit of attention to the signs. I'm actually going to set up our mapping statement first, though, before I kind of talk about signs. So we'll do X, Y, and then maps to, and then because the numbers are changing, that means the X and Y coordinates are switching. So I'm gonna put Y, X, and then we're gonna go back and add a little bit to this. So one more time with like the values changing, I'm going like 4, 3 to 3, 4, 1, 3 to 3, 1. So the X and Y coordinates are switching. And then now we can kind of worry about how to incorporate the signs. So it looks like on, say, point M and M prime, the original Y coordinate was 3, and then that became like the first coordinate over here, but that got made negative. And then the original Y coordinate here was 3, that became the X coordinate over here, but it got made negative. So I'm going to say that this maps to negative YX. And then we can just double check to see if we need to put a negative over the X. So if that's the case, we had, so X over here became the y over here or the second coordinate over there. And on all of those, like the signs are not changing. They're staying negative as they originally were. It's just the, oops, sorry. It's just the original y coordinates that we're switching. So like over here, that was my original y. It became negative over here. It became a negative right here. It became negative right here as a first coordinate. So we have to put the negative over here on the first coordinate. Okay, so xy maps to negative yx. And then down here, I would just like screenshot this, write it down, put it somewhere where you can keep it handy. It's just some shortcuts for writing mapping statements for rotations, because you can kind of see it would be pretty hard to write this mapping statement if we didn't have this table of points. And if we weren't given the table of points, if we were just writing them down each time, that would probably be pretty time consuming. So these are just kind of a shortcut to help you do it a little bit quicker. So I'm going to use the one we just kind of did. So it says rotate a point xy 270 degrees clockwise or 90 degrees counterclockwise about the origin. So we just did 90 degrees counterclockwise, and like I was saying, you can always describe it in more than one way. You can also, sorry, I don't know why that keeps crossing out clockwise, but you can also describe it in the opposite direction, and then it would end up being sometimes a different degree measurement. So 90 degrees counterclockwise is 270 degrees clockwise. That's one we just did, but the rest of those are here so that you can always kind of come back and reference them really quickly. Okay, so starting from the top, I'm just going to go through this really quick. If you rotate a point 90 degrees clockwise, that is the same thing as 270 degrees counterclockwise. And if that's the case, the x and the y switch, so it maps to y, and then negative x. And then on the second or upper right one, rotate a point xy 180 degrees clockwise or counterclockwise, because 180 degrees is like halfway around a circle. So it doesn't matter which direction you go. If you go halfway around a circle, you're going to end up in the same exact spot. So these points would map to, they stay the same value, they just switch to negatives. So xy maps to negative x, negative y. We already talked about the lower left. That's the example that we just did. And then the lower right, rotate a point 360 degrees clockwise or counterclockwise. So that's one full rotation. So it does not matter which direction you're going. If you go one full rotation, you're going to end up at the exact same spot. So xy would map to xy because it's the exact same spot. And then on to 6.3, this one just has the one example. So series of transformations, that's when you have to incorporate multiple transformations at once. So rotate trapezoid ABCD 90 degrees counterclockwise about the origin, and then translate it 3 units down. So order does matter here. So get into the habit, don't just pick which one you want to do first. You have to pay attention to what order is given to you in the problem, and you need to do it that same way. More times than not, it will give you an incorrect answer if you do it out of order. So the first thing we're going to do is rotate, because that's the first thing it tells us to do. And then it says then translate it 3 units down, so that's the second thing that we're going to do. So fortunately, we have all of our shortcuts here on the same page. So we're going to rotate 90 degrees counterclockwise. So for 90 degrees counterclockwise, that was this one. So we can use that mapping statement just to get our new points. I'm just going to write it down here so that I can kind of zoom in and reference it a little bit easier. But to rotate 90 degrees counterclockwise, xy maps to negative yx. And I think it's kind of hard to like draw a rotation on a graph without seeing my points. So I'm just going to go ahead and kind of make a table like we did up here for this example, or like that was given to us up here. Okay, so I'm not going to set up the full table, but I'm just going to list my original points. So let's see, A was the point over here, it was 3, 3. And then B is 4, 3. C 4, 1. work ahead of me if you're good. And then D was 2, 1. And then now I need to get A, B, C, D prime, so just the new version of those points. So in order to rotate 90 degrees counterclockwise, I have to switch the X and the Y coordinates, and then the new first coordinate becomes negative. So these are both 3s, so if I switch them, it would stay 3, 3, but this is going to become a negative 3, 3. And then for B, and this was A prime, sorry, I forgot that. For B prime, I switch the X and Y, so it become 3, 4. First coordinate becomes negative because this becomes negative up here. And then for C maps to C prime, I switch the X and Y, so it becomes 1, 4. The first coordinate is now negative also. And then for D prime, I switch the X and Y, so it becomes 1, 2. The first coordinate becomes negative. So these are all my new points. I'm going to go ahead and add them to my graph. So for A prime, it was negative 3, 3 up here. And then for B prime, it's negative 3, 4 up here. And then for C prime, negative 1, 4. And then for D prime, it's negative 1, 2. And then I can connect those. And then now I can worry about my translation. So for translating 2 units down, or sorry, 3 units down, I don't think we necessarily need a mapping statement for that. I think we could just count the points down a little bit easier. I'm going to move them all the way down. I'm just going to incorporate like a double prime to show the difference between like my middle image and my final image. So if I want to move A 3 units down, I can just count it 1, 2, 3. So it'd be right here. I'm going to use a double prime just because I did 2 transformations. And then for B, down 1, 2, 3 right here. This is B double prime. Double prime feels a little silly, but it's okay. And then for C, move down 1, 2, 3, so it'd be right here. This is C double prime. And then for D, move down 1, 2, 3 down here. So this is D double prime, and then we can connect them. Okay, so main takeaway here is just the fact that if you have multiple transformations, you just have to make sure that you do them in the correct order. You have to do them in the order that is given. For this one, for example, I'm not going to do it in the video because just to save a little bit of time for you guys, if I did this in the reverse order where I did the translation first and then the rotation, I would end up with a different final answer.